In previous videos, we've explored monopole, dipole, Yagi, and LPDA antennas. I have a link in the description to those videos if you haven't seen them as yet. Today, we'll take a close look at the Bowtie antenna, a variation of the dipole designed for wideband applications. This video is for those of you who want a more technical understanding of the Bowtie antenna. We'll calculate the bandwidth, determine the element's length, and show you how to design a Bowtie antenna with the correct impedance and bandwidth. By the end of this video, you'll have all of the tools to design your own Bowtie antenna. Let's get started. First, we're going to look at the flare angle. This is what sets the Bowtie antenna apart from the dipole antenna. The flare angle is the angle between the two arms of the antenna. Let's start with the extreme case, which is at 180 degrees. Now, this Bowtie antenna is at 180 degrees. Much like the dipole antenna. The dipole antenna just got two elements straight across here at 180 degrees. What makes the Bowtie antenna different is the flare angle. Each one of these corners rise up by 45 degrees. So here we have the first angle from 0 to 45 degrees. The second angle here would be from 135 to 180. Which would also be 45 degrees. And the third angle would be from 180 degrees to 225 degrees, which would also be 45 degrees. And the last angle would be from 315 to 360, which is back to 0 here. So from 315 to 360 would also be 45 degrees. So each one of the angles would be 45 degrees, and if you multiply 45 by 4 angles, you'll get 180 degrees. And all of the flare angles work in the same exact way. And you'll also notice that as we increase the flare angles, we also increase the bandwidth. As for the Q factor and the impedance, don't worry about these. We'll be using these in order to do the calculations for this antenna as we go through this video. Now we're going to calculate the bandwidth of this frequency of 500 megahertz. This is our resonant frequency. This is the frequency that's going to be sent out from your transmitter to the antenna. So your data is going to be riding at this frequency. And in order to send data, we need bandwidth. So the bandwidth makes up the upper sideband and the lower sideband. So you'll have higher frequencies on this side and lower frequencies on this side, which is the lower sideband. Okay, so the more bandwidth you have, the more data you can send. So how we calculate bandwidth is with this equation. Bandwidth equal to frequency over Q. Now we know what our frequency is. It is 500 megahertz, but we have no idea what is Q. And to give you an idea what Q does, Q is how we measure how sharply an antenna resonates at a specific frequency. It tells you how much energy is stored versus radiated by the antenna. So let's find out what our Q is for this antenna in order to find out what is our bandwidth. Now here we're going to be calculating the bandwidth. Bandwidth is equal to frequency over Q, as I said before, and we have to find the Q. So over here I have the equation for Q. So Q is equal to 1 over K times tan times the angle divided by 2. K is the phase difference between the elements. The numeric value for K is between 0.3 and 0.6. For the bow tie antenna, we use 0.4. So on this line, I have Q is equal to 1 over 0.4, replacing K with 0.4, times the tan of 90 degrees. See, the angle is 90 degrees, and we're going to be dividing that by 2. So we're using 90 degrees here because 90 degrees is the best trade-off angle between impedance and bandwidth. So 90 degrees is the best angle to use for the bow tie antenna. So the next line here, we have Q is equal to 1 over 0.4 times the tan of 45 degrees. I divide 90 by 2 and I got 45 degrees. So in the next line, I have Q is equal to 1 over 0.4 times 1. Now the tan of 45 degrees is 1. I just type 45 degrees into a scientific calculator and hit the tan button, and you would get 1. So in the next line, I have Q is equal to 1 over 0.4, which is equal to 2.5. So Q is equal to 2.5. So over here, I substitute Q with 2.5. So I have 500 divided by 2.5 gives you 200 megahertz. So here we have our resonant frequency of 500 megahertz down the middle. And this side is our lower side band and this side is our upper side band. So we divide this 200 megahertz and place 100 on this side and 100 on this side. So we will subtract 100 megahertz from the 500 megahertz on this side. So we'll start at 499,999,999 hertz. And we'll move all the way down, subtracting 100 megahertz from that 500 megahertz until we get to this end, where we'll have 499,999,900 hertz. So on the lower side band, we subtract 100 megahertz. On the upper side band, we add 100 megahertz. So we start at 500 million and 1 hertz, and we move all the way up to 500 million 100 hertz. So this represents our entire bandwidth of 200 megahertz. So now we need to determine the length of each element. That is the length of the sides here. This is side 1, 2, 3, and 4. Now, in order to determine the length of these sides, the first thing we need to do is to figure out what the wavelength is. So the wavelength is equal to C over F. C stands for the speed of light, which is 300 million meters per second. And the frequency, which is a resonant frequency, is 500 million hertz. So if we should divide this 300 million by 500 million, we would have 0.6 meters. Now this 0.6 meters is a full wavelength. Now we need to divide this 0.6 by 4 in order to get the length for each one of these sides. So under here I have antenna's length is equal to 0.6 divided by 4 equals 0.15 meters, which is 15 centimeters. So these 4 sides are all 15 centimeters in length. So the next thing we need to do is to calculate the exact triangle size. Now we already know the length of these sides here, but we don't know the height of this vertical side. The height is important because in order to have the antenna at 90 degrees, as this antenna is supposed to be, you got to know what height it's supposed to be. So in order to do so, we use this equation. H is equal to L times the cosine of 90 degrees divided by 2. The next line will be H is equal to 15. 15 is the length of these sides, which is 15 centimeters. 15 times the cosine of 90 divided by 2 is equal to 45 degrees. So the next line would be H is equal to 15 times 0.7071. Now the cosine of 45 degrees is 0.7071. You just type 45 into the scientific calculator, hit the cosine button, and you would get 0.7071. So now if we would multiply 15 by 0.7071, the answer would be 10.61 centimeters. So the height here is 10.61 centimeters for both sides. So now we know the length of these sides and we know the height. So we can actually go ahead at this point and cut the metal that we need. It could be aluminum or copper that we would use by 10.61 in the height and 15 centimeters at the sides into a triangle shape like we have here. The next important dimension to calculate is the small gap between the elements. This gap here. This gap is critical for proper feeding and impedance matching. The gap should be 1 to 2% of the full wavelength. Now under here, I have this equation. Gap is equal to wavelength times 0.01. So I'm using 1% in this case. So the gap is equal to 0.6 meters, which is the full wavelength, times 0.01, which is equal to 0.0006 meters, or 0.06 centimeters. So as I have written here, the gap is equal to 0.06 centimeters. Now next we want to calculate the impedance of our antenna. It's very important to know the impedance because you want to have some sort of impedance matching, like your coaxial cable may be 50 ohms or 75 ohms, and you want to match it to your antenna, and you need a Balun. So in order to know what type of Balun you would need, you need to know what's the impedance of your antenna. Now here I have all of the information that I would need in order to calculate the impedance of the Bowtie antenna. Now here I have the length of each arm, which is 0.15 meters, and the gap is 0.6 centimeters. This is information that we have just calculated. And 60 is a simple constant based on electromagnetic field theory. So this is something that you would always use. You don't have to calculate this. This is a given. Okay, so over here, Zn means impedance in. This is the impedance of your antenna, which is equal to 60 times Ln. Ln is a trigonometric function that we're going to be using. I'll talk to you about that in a second. And this is times 2L. L stands for the length, which is this length here. 0.15 meters. This is the length of your element. So we have 2 times L divided by G. G is the gap. That gap between the two elements, 0.06 centimeters. Under here we have Zn equals 60 times Ln times 2 times 0.15 meters divided by 0.0006 meters. So this is in meters instead of centimeters. This is the gap, but I have it here in meters. Since I have everything else in meters, got to keep it all in meters, so I just change it to meters. So Zn is equal to 60 times Ln times 500. Now I got 500 by doing my multiplication and division here. 2 times 0.15 meters divided by 0.0006 meters, and I get 500. My next step here, Zn is equal to 60 times 6.2146. How do I get 6.2146? Well, I just type 500 into the scientific calculator and hit the Ln button. Okay, and you would get 6.2146. So for Zn, it would be 60 times 6.2146, and my answer would be 372.88 ohms. So my antenna's impedance is 372.88 ohms. Now we're going to talk about Balun transformer. Now there are two reasons why you would need a Balun transformer. Let's say your coaxial cable and your antenna's impedance was matching. They're both 75 ohms. They're not in this case, but let's say they were. You still couldn't connect your coaxial cable directly to the antenna because your coaxial cable is an unbalanced medium and your Bowtie antenna is a balanced medium. So you cannot connect an unbalanced medium to a balanced medium. You'll get some undesirable results. So in that case, even if they were the same impedance, you would need to use a 1-to-1 Balun transformer. But in this case, the antenna's impedance is approximately 4 times higher than the coaxial cable. So in this particular case, I would recommend using a 4-to-1 Balun for this antenna that we've just designed. Now your antenna is built and you really don't need this final step to do anything with the build of your antenna. The reason I'm giving you this information is simply because of antenna modeling. The software will sometimes require this information in order to model your antenna. So I'm going to calculate the flare width, which is called the W. This is the width from one tip here over to this tip. So in this case, it's 21.2 centimeters. And I'm going to show you how to calculate the W of an antenna, since you'll need this information for some modeling softwares. So the W is equal to 2 times L, which is the length of the element, times the sine of 90 degrees divided by 2. Okay, so W is equal to 2 times L, which is 0.15 meters, times the sine of 45 degrees. So I just divide 90 by 2, got 45 degrees. So here I got W equals 0.3 times 0.707, which is the sine of 45 degrees, 0.707. So I just multiply 0.3 by 0.707, and I got W equals 0.212 meters, which is 21.2 centimeters, and that is what I have above here. So this information is needed when using some modeling softwares. And modeling softwares that you could use are CST Studio, HFSS, EZNEC, or 4NEC2. 4NEC2 is a free modeling software. The other ones, I believe there's a charge for those ones. You might want to take a look at 4NEC2 if you're new to software modeling, and you might have to download it and install it onto your computer. I believe that this software works with PCs only. I don't believe that it actually works with the Mac. But you can check that out again. But I don't believe the last time I checked it, it was actually working with the Mac computers. It was just PCs. So that's it, guys. I hope this video was helpful to you. I really do. And if this video was helpful and you would like to see more videos like this one, please don't forget to like and subscribe.